Hello, and welcome to this W3C breakout session. The goal here is to revisit the open questions regarding in-band extracts in MediaSource Extensions. My name is Alicia Boya Garcia. I work for Igalia, and I'm part of the W3C Media and Entertainment Interest Group. First, I would like to remind all the participants of the participation policies of the breakouts this year, in particular the Code of Ethics and Professional Conduct and the Antitrust and Competition Guidance. The URLs for them are in the screen and in the slides that are already available in the GitHub issue, as well as in the page of the W3C breakout session. For this presentation, I'm going to assume you have some familiarity with MSE, also known as MediaSource Extensions, but I'm not going to assume a specific knowledge about extract formats. To clarify, when in this presentation, I will be talking about out-of-band extracts. I am talking about formats that are purely for text tracks. They are often textual, and examples could be the SRT format or the WebKit format. When I'm talking about in-band text tracks, I'm talking about text tracks that have been put in a media container file, like MP4, WebM, or Matroska. The same file, because of this, can also contain video and audio, but it also doesn't have to. And in fact, we have the example of Matroska, where this is common enough that it warrants its own extension. So MKS files means that this is a container file used specifically just to handle text tracks, but no audio and video. The agenda for the meeting is split into two parts. In the informative part, I will be giving an introduction to WebKit, in particular the features that make implementation of in-band tracks in MSE and in containers in general a bit more tricky. And I'll also explain how those representations inside container formats work. Then I'll go through a lot of challenges and open questions regarding the implementation of text tracks in MSE, many of which are consequence of container representations, but not all. So let's start with WebKit. WebKit is the web video text tracks format. It has been supported in browsers for a long time. And it's a reasonable first target because it's been quite successful in adoption. So it would make sense that if we support it already in regular playback, and we also support it as an out-of-band text track format, including when the video is MSE, that we could also support it in band when it's part of the data being downloaded and pushed into append buffer. The basic syntax of WebKit is something like this. It's intentionally inspired by the subrip format or SRT. We have a file header that identifies that this is indeed WebKit. And then we have a series of so-called queues, which have a start timestamp, an end timestamp, and content, which can be not only text, but it can also include markup for styling. Each queue can also have settings. And here we have an example where we have customized the position of the queue and the alignment. Queues can also have IDs. These IDs can be used for styling, and they are also accessible to JavaScript. This is a very important difference with video in that when you load text tracks in web APIs, you are able to access the list of queues, its contents, and you have access to certain metadata like these IDs. So they can be retrieved and controlled programmatically. WebVTT also supports comment blocks. These are not rendered, but they can be very important for people authoring text tracks. So container formats will generally try to preserve this. WebVTT documents can contain an style sheet. The style sheet is global for the entire document and must be placed at the beginning of the file before any cues. Another feature that is structure similar is regions. Regions allow to define specific portions or regions of the video where cues will appear. WebVTT allows timestamps or allows cues to overlap in time. So here we have an example where imagine we are doing closed captions. So we don't have only the dialogue, but also textual representations of sound effects. And those often happen simultaneously. So we need to be able to show two cues at the same time. The format natively supports this, so we'll see container representations can be more complicated. And maybe the oddest format, the oddest feature is that inside a queue, we can have delayed parts. For instance, the first queue here, the good evening and is anyone there form part of the same queue. However, the second part is only shown at the specific timestamp between angled brackets. That's it for the features we are going to consider about WebVTT for being particularly of interest for containers and therefore of consequence to MSC. If anyone have any questions to this point, you are very welcome to ask. No questions? I will continue. So now let's look at inbound WebVTT. That's when we place it into inside a container format. And at the moment, I am aware of two formats that supported. We have the ISO-based media file format, of which MP4 is derived from, and which I'm just going to call MP4 for the rest of the presentation to make it easier to pronounce, even though it's technically not correct. And then there is also WebM and Matroska, similar to ISO-based media file format. WebM is derived from Matroska. So this way, this time is the opposite relationship. WebM is a subset of Matroska. And we'll get to them. We'll get to them. Unfortunately, I'm not aware of any representation for MPEG 2TS. Let's look at how WebVTT in MP4 works. We have things split into two different specs. On one hand, we have the base spec for ISO-based media file format, but WebVTT encoding is specified in a different part, in part 30, along with TTML. Codecs, the codec string should contain the 4cc WebVTT to represent that this file will contain a WebVTT track. And in MSC, this is the 4cc that you would also use in append buffer. For the initialization segment, which in MP4 is the move box, we get a WebVTT specific sample entry, which again, despite its name, it's more like codec configuration. And it contains two boxes inside. The first one, WebPTT configuration box, contains the file header. This is the first line with WebPTT and any style sheets, regions, and any other similar features that get introduced in the future in textual format. Then, optionally, but we'll see importantly, we have source label box. This is meant to be an opaque URI that uniquely identifies this WebPTT document. And the idea is that two different WebPTT documents will have different source labels, and the same WebPTT document in different MP4 files, if we are cutting them into pieces or whatever other manipulation, would still have the same source label. For the media segment, the timing of the queues is handled entirely by the container. So the timestamps we saw in the textual WebPTT format are not stored inside the frames or samples. Frame and sample mean the same in the context of MP4. Instead, it's handled like regular video frames. However, the biggest difference is because WebPTT allows several overlapping frames, several overlapping queues, but MP4 doesn't. It's not meant to be used that way normally. The queues are split into continuous non-overlapping frames. The frames are ISO BMFF boxes inside, and we'll see what they contain. We'll have two types of frames. We'll have gaps, which represent the absence of a queue for the duration of that frame. And we have non-gaps, where we will have one or more PTT queue boxes and optionally PTT additional boxes. These are currently used for notes, for comments. And they would be inserted for the adjacent queue after which they appear. Now, let's look inside PTT queue box. Remember, we can have multiple of these in a frame. For each one of them, we have optionally a source ID box. And together with the source label, this allows us to uniquely identify a queue. Because queues are split into continuous non-overlapping frames, the same queue might appear on multiple frames. And therefore, we need a way to be able to tell apart that this queue box and this queue box actually represent the same queue and not two different queues that happen to have the same contents. This is what the source ID box allows us to do. But the ID of a queue is not just the source ID, but also the combination. It's the combination of the source label and source ID. So that if we mix and match different WebPTT documents that have been moved to MP4, we don't accidentally treat two different queues from two different documents as the same just because they happen to coincide in the same source ID. And other than that, we mostly have different boxes with different parts of WebPTT queue. So payload contains the text of the queue with any markup. Settings contains the line of settings that I saw in an example before, if there is any. And a queue time box is used in the case of having queues with delayed parts. And the way it works in MP4 is that you write there the original start time of the queue so that the decoder is supposed to use this time as reference to compute the actual times of the delayed parts. So that if there is an edit list or in any other way the timestamps of the frames are changed, delayed parts still work. Now, for WebM, the first problem we find is that there are two competing representations. There is one from the WebM project that was proposed around 2012, at a point where WebPTT was still relatively immature, but still got adoption by software. So this is the one currently supported by FFmpeg, for instance. As a consequence of coming so early, it didn't account for the file header. In particular, this means that we cannot support CSS or regions. It also doesn't account for what to do with queues with delayed parts. A later standard came from Matroska, which is the parent format of WebM. And the first draft I found is from 2018. And it actually addresses those two problems of the other representation. So the header actually goes in the codec private, which is similar to what we saw in MP4. And the encoding of queues with delayed parts is specified how it should be done. It uses a different method. Instead, you don't write the original timestamp for the time of the delayed part. You write the offset from the start of the frame. But that's it. It's just a very reasonable way of doing the same thing. Now, important differences between the WebM representation and the MP4 representation. And all of these are common to both representations. Here, one queue equals one frame. Overlapping queues are encoded as overlapping frames. Matroska uses a different structure than MP4, and this is easily handled, at least by the container format. And for similar reasons, caps are not explicitly encoded. Also, because we don't have any equivalent of queue IDs, there is no provision for how to join queues split at segment boundaries. If you use, for instance, MKB Toolnix, which is a typical software for splitting Matroska files, it will just try to cut in a way that avoids cutting any queues. And that's it for in-band representations of WebPTT. Are there any questions so far? It's a lot to tackle, and I'm not expecting it to be easy to process this quickly. For the rest of this talk, I'm going to go through several questions. These regarding to these are related to MSE and test tracks, both with WebPTT as an example, but also talking about other topics that are tangentially related. The questions I'm asking that are a bit open-ended and of particular interest are both bold and highlighted in green. So, first one. How many coded frames is a WebPTT queue? A coded frame in the MSC spec roughly corresponds to frames in a container. But as we have seen, different containers handle this differently for the same format, in this case, WebPTT. So what should be the case for WebPTT queues? Should we also have a one-to-one, one MSC coded frame, one WebPTT queue, like WebM and Matroska? Should it be depending on the container format? Should it be an implementation detail of that particular user agent? Or maybe something else? Maybe having them overlap as consequence is not something we want, and then we actually want something more like MP4, but for all formats? And how could that happen? There are many open questions here. And I don't expect easy answers. And any answer to this question is going to touch many other questions. So I'm going to continue. And the next big question is about gaps and sparse streams. So let's consider the case of WebPTT in MP4. And you might remember we saw a PTT empty queue box. That's what we put in a frame where we have a period where there is no queue. Is that an MSC coded frame? The answer to that could be very dependent on the previous question. And thinking more about gaps, we might also want to consider that there are other formats that work differently. For instance, looking at text track formats, there is 3GPP time text, which is very commonly used in MP4, way more common than WebPTT, where gaps are actually encoded as queues with empty text. But since the format is a bit simpler, this is an acceptable solution for that particular format. So if a browser wanted to support 3GPP time text in MP4, which might not be that unreasonable, given that it's not that of an uncommon format, could those gaps be queues? What would they be? And of course, we also have container formats. MP4, due to its particular structure, makes it easier to encode gaps than explicitly than to not do it. But in Matroska, that's not a problem, and the representations that currently exist don't do it. So is that a problem for MSC? It definitely causes some difficulties. And talking more about gaps. Gaps are not just a useful concept in text, but they also generalize to audio and video. An audio gap is an intentionally silent section because there is no data to be played. And a video gap is just no new frame is played. Either you would see the continuation of the last frame or some replacement image. And this I'm talking in the abstract, not particular implementations. Now, there are already some use cases for MSE where gaps could potentially be useful. And we have talked about them in previous W3C Media and Entertainment Interest Group meetings. One of them is live playback. So for both of these, imagine you have audio and video in separate source buffers. And for the first case, imagine that you are watching a sports event. In these kinds of events, you often prioritize having the latest information to getting all the information. So for a player application, it's desirable that if for some reason you are unable to download a chunk of video on time, but you have the audio, at least you can play the audio. And this is something that could be implemented with gaps, but this is currently something that does not exist in the MSE spec. So I'm bringing this up because if it's relevant for text, it might also be relevant for other types. The other use case is, imagine you again have separate audio and video, and you want to insert an ad or any other kind of interlude where you only have one of the two. So you need to transition from video and audio into a segment that is only video or potentially only audio, and then back. Gaps could also work for that potential case, in particular when tearing down the media resource is not desired by the user. And then, more related with gaps, we have the little problem of the source buffer with only a text track. This is currently de facto unsupported, and it's just a consequence of this lack of support of explicit gaps. Buffer ranges are computed only from video and audio because the current MSE spec assumes that text streams will be sparse and will have unannounced gaps. So to compensate for this, the buffer ranges algorithm doesn't include text tracks in the computation. As a consequence, if you have a source buffer that only has text, the buffer ranges never grow, and you have a source buffer that never buffers. So playback cannot start. We could talk about whether it could make sense to work around this by just not including any source buffers that only contain text tracks in the computations, but even this could also have some problems because for many use cases, if you have not buffered text, you don't want to play. Imagine you don't understand the language or you cannot hear it. You would want playback to wait for actually getting the subtitles or captions. So it could actually make sense to block playback for them in many circumstances. But because we don't have explicit gaps, we cannot do this at the moment. Or at least we can only do it if we have also audio and video in the same stream to guide us. Now, abandoning a bit the thing about gaps frames, let's consider queues that go across segment boundaries. So, imagine we are splitting some MP4 file for adaptive streaming. We would be cutting the file into segments. And thanks to the source label and source ID, we can identify the copies of the queue in different fragments. And we can tell that this queue from the new fragment is the same as a queue from a previous fragment, and just extend the queue. However, the MSC spec does not specify this at the moment, and it also, as a consequence, makes no mention of whether this should be indeed how it should be handled, and whether it's mandatory or whether this is a quality of implementation issue. And there is also a minor question of how should that extension of the queue be presented. I think the way that makes the most sense is to change the duration of the queue and or the timestamps and emit an on-queue change. But this is something the spec should clarify. And in WebM, we have these problems that we mentioned earlier. At the moment, the MSC WebM bytestream spec doesn't tackle them at all. So we are not picking a side in STEX versus in whether we should be using the original WebM representation or the later Matroska one that has fewer problems. And it could be argued that maybe we should, but we could also discuss, and this might be depending on conclusions from other discussions, whether the representations that WebM and Matroska give us are good enough. Whether we, for instance, we could want explicit gaps. And these are changes that we could advocate for because these are open formats and you can actually write to the mailing list of IETF and, for instance, add optional features and use them in MSC, or even if found interesting or necessary for the spec, even require them, as we are already doing with them before. Then there is a whole discussion about embedded text tracks. And there are two that I'm giving here as an example, but they are also common examples. One is CA 608 and 708. And generally, the problem with embedded text tracks is that we don't know we have them in advance. They are a bit of a surprise. In the case of CA, they appear inside the video. And even when this is not the only way to represent these types of tracks, it's often done for compatibility reasons. There is also ID3 time text, which has a similar problem. It's not structured as a track, but instead as interleaved chunks between fragments in the case of MP4 or between transmissions in the case of MPEG-TS. And this has been discussed before, and but support has not arrived for MSC. So it might be interesting to keep these things in mind. And that's it. That was a lot. I'm sure that was very overwhelming. But these are the problems and open questions that I have identified so far, thought could be interesting to discuss as we try to mature the support of time text tracks in MediaSource extensions. We can go back and discuss.